Since this discovery about 20 years ago, we've done at least one good thing, and that's to give this catalyst a name: dark energy. And to be honest, it's a pretty bad name. For some reason, in science, whenever we find the existence of something that we don't know how to handle or have no idea how to explain, we just say it's dark. It isn't dark, it's unknown. When scientists and physicists alike mention dark energy, they mean the unknown form of energy that permeates throughout the entire universe, which also sequentially causes the universe to expand at an accelerated rate. Dark energy is literally everywhere. To explain, imagine a fish tank. Inside, you have fish, maybe some plants, some logs, a couple rocks. You get the idea. Imagine that this fish tank is the universe. All of the fish and other things inside the tank are ordinary matter, which are things like you and I and everything else you see in life. This includes buildings, galaxies, stars, plants, dogs, planets, so on. It's all considered ordinary matter. However, the fish tank isn't only filled with just ordinary matter. It's completely engulfed in water. The water fills every nook and cranny inside the fish tank, and yet all the ordinary matter inside still remains. There's much more water than anything else in our fish tank universe. The amount of water is similar to the amount of dark energy in the universe. Now, of course, the water in our fish tank isn't expanding the tank, and the water itself is actual matter, but it is a good way to visualize it. It's everywhere at once, and in relatively the same amount. There's a theory about the way dark energy works and why it seemingly causes the universe to speed up, to accelerate. An idea is that dark energy could just be a property of space. It's the idea that empty space isn't actually empty, it has energy. It's a very small, almost infinitely small amount. But it's not zero, and that's very important. And as we know, all normal matter, all elementary particles that make up everything you know, is already 99.99% empty space in itself. Everything we see is made up of almost nothing. There's matter that interacts with light and that we humans can interact with. We can see it and touch it. But even empty space, something that we tend to ignore, has properties that could explain dark energy. At the smallest levels imaginable, at the size of protons, empty space isn't all so empty. It's full of quantum field fluctuations, which represent the smallest amounts of energy changes at any specific point in space. To keep things brief and basic, they may be caused by virtual particles that come into existence in pairs of electrons and positrons with opposite charges. Because of this, they immediately annihilate one another, and they release small amounts of energy. This isn't a joke. Physics, Heisenberg's uncertainty principle, actually allows for this. The law of conservation of energy doesn't apply to an expanding universe on huge scales, only in a static environment, one that is relatively unchanging. This visualization is kind of like an energy map. The dark red spots indicate high energy densities. This is most likely where these annihilating particles are conducting their business. This helps to visualize the fluctuations, but the speed is unmatched. It actually isn't even close. This is running at a septillion frames per second. For example, most movies you watch are at 24 frames per second, and you're able to follow that very well. These fluctuations you see are occurring at unbelievable speeds. In the vacuum of space, the nothingness of space, this is happening right now. Everywhere. The amount of dark energy in every cubic centimeter of space, about the size of an earring, is about 10 to the negative 8th ergs. The units don't really matter here. But to compare, dropping a penny from waist height hits the floor with an energy of about 300,000 ergs. That's over 1 trillion times more energy. This makes dark energy look puny. However, its most important feature is that it is literally everywhere. This tiny amount of energy adds up very quick. As the universe expands, more space is created, like the universe is an infinite plane that continues to stretch and stretch. Dark energy doesn't dilute away over time, it stays uniform. Like I said, the easiest way to explain dark energy at this point is to just say that it's a feature of space-time itself. It just exists. Dark energy is stretching the fabric of space-time. Imagine taking a bedsheet and continuously stretching it out forever and ever without it tearing. Now normally this expansion doesn't make much of an effect on local matter like stars and planets and so on. Gravity is strong enough to hold all of this together. However, light itself is actually vulnerable to this stretching. Edwin Hubble noticed this in 1930 when observing the far reaches of our universe. Hubble's law shows that when you're observing objects extremely far away, in extragalactic space, the light you receive is actually altered in a way. Because of the extreme distance, the wavelengths of light are literally stretched out along with space itself. The largest visible wavelength that we can see is a deep red, and that's exactly what we saw when we looked to the far corners of the universe. You can still see that today, actually. Remember, on small scales, gravity is strong enough to keep the solar system and planetary systems held together, but on large galactic scales, not a chance. Dark energy has a negative pressure, which basically just means that energy is gained as the universe expands. There's more of it every second. There's more space, so that means there is more room for these fluctuations to happen, which means the universe will expand faster. Dark energy, at least according to our current calculations, will eventually push every galaxy so far away of us at such a high speed, even faster than the speed of light. The light emitting from these galaxies will travel towards us at light speed, but even this won't be enough, and the light will never reach us. It will spread the universe so thin that when you look out to observe what's around you, you won't see anything. This is very possible and can actually happen, although it goes against your intuition and education on the subject. Space itself can expand or contract at any rate, but the things in space are subject to the cosmic speed limit of light. We're incredibly lucky to live in a time where we can explore phenomena such as dark energy. We may have been born too early to travel the galaxy, but we were born at the perfect time to explore something even larger, the universe we inhabit, and the rules that govern it. According to physics, the entire universe and everything in it, us, the Earth, the Sun, the Milky Way, it can all be described with a few set of equations. Nobody said they were easy equations, but we have them nonetheless. The most interesting part, however, are the so-called constants in our equation. Numbers like pi, e, the golden ratio, the gravitational constant. Why are these constant? Where did they come from? The bigger question here is, are these values truly constant, or do they vary over time? If they vary, then their values over time would have to be determined by yet another equation, and this would change everything we know about the universe at the moment. If even one of the fundamental constants isn't actually constant, it would open doors to entirely new subfields of physics. But what if I told you that one of the most important constants, one that explains the modern universe, may not actually be so constant? That when tested and measured in different ways, it yields different results. Albert Einstein published his theory of general relativity in 1915, and to this date, his theory is still accurate and upheld. However, the interesting thing is, at this time, there was no evidence that the universe was expanding. A theory that so eloquently describes the universe and our place in it is based off of a static universe, one that's unchanging over time. But when the theory is applied to a static universe, one that Einstein believed we lived in, the theory falls apart. It won't allow for a universe that is unchanging. So, he introduced a term that would fix this, a number that would counteract the effects of gravity, but yet keep the same results. This term is lambda, or more commonly known as the cosmological constant. But in 1930, Edwin Hubble observed galaxies far, far away from Earth. When observed, these galaxies had a visible redshift in their appearance, indicating that these galaxies were moving away from Earth, and the further away they were, the faster they were moving. Considering how far away these galaxies are, the light that emits from them takes a long time to reach us on Earth. These light waves are literally stretched out, and because the color red has a longer wavelength than all other colors, it results in a visibly red hue, just like we mentioned earlier. This is direct proof that the universe is not static, but is rather expanding. This makes the cosmological constant basically useless. This is Einstein's biggest blunder. If he had just left this term out of the equation, he would have literally predicted the universe's expansion. But instead of trusting his original theory that was literally telling him the universe was expanding, he introduced a term to stop it. It wasn't for another 13 years that Einstein would learn that his cosmological constant was unnecessary, and then removed from his theory. Imagine an extra 13 years on Einstein's life, and what discoveries could have been made. For 60 years after the discovery of the expanding universe, the cosmological constant was set to 0. We didn't need a number to counteract the force of gravity to keep the universe static, so we got rid of it. Until Saul Perlmutter showed up and discovered that the universe was accelerating. It was growing at a rate that wasn't constant. This changed so much in our theory that lambda, the cosmological constant, is back in our equations today. We can interpret the cosmological constant as a property of space itself, of the empty space where nothing happens. But this actually drives the universe. Dark energy is already dominating the expansion of our universe, and it has been for a while, for over 6 billion years. For over 80 years, the cosmological constant was seen as a failure, as a mistake and a useless part of an otherwise perfect theory. But today, it helps us explain the driving force behind our universe's expansion. This blunder is what allows us to understand what nearly 75% of our universe is made of, without us even being able to see it. It describes something that is hiding before your eyes at this very moment. 5% of the universe is the most that we could ever visually see with our eyes. 27% is made up of dark matter, which is an entire other beast that deserves a video of its own. The remaining 68% is assumed to be dark energy, whatever that may truly represent. Based on historical examples, almost every theory we've had about the universe was wrong at the start. Not necessarily wrong, but just incomplete. As time goes on, we get more and more accurate with our predictions and our theoretical models. Einstein's biggest blunder is actually one of the biggest ideas in modern physics. This kind of proves that science is about making mistakes, because the biggest mistakes yield the biggest breakthroughs. Everything you've ever seen with your own eyes or ever will observe is made of ordinary matter. Every person you ever met, every planet you observe, is made of ordinary, regular matter. 95% of the universe we inhabit is ruled by forces we cannot explain. But each day, each experiment, each theory inches us closer to the day where we're finally able to explain the mysterious force throughout our universe. And when that day finally comes, science, and subsequently mankind, will change forever.